Hello, folks. Let's see if we have anybody on. We have 10 people. Wonderful. Excellent. Okay. So I was looking at Piazza just a few minutes ago, and there was a question about, will we have a bonus for assignment 6? Yes, that bonus is out. It's on the GitHub now. There's also a reply from Max about where to find the link. Let's see here on Piazza. Is the answer key available for fall 2019 final? Yes, there is. It is on Canvas. They made the solutions available. You can also check Piazza for it. Should be there as well. Should be part of, yeah. So as part of the week 14 announcement has a link with the exam and the clarifications. Let me click on that and make sure that's actually correct. Oh, now it's making me log in, and it'll make me do two-factor. Jeez. All the modern inconveniences. There we go. Yep, indeed, the solutions are there. And I believe also, yeah, solutions are there. Great. So that's confirmed. Okay. Now, what else do we have in that one? Let me reload, make sure. There's nothing else on that Piazza. Whoops, I'm on the wrong place now. Okay. Office hours for today. Okay, so that Piazza is fine. Let's look at that was P. Let's look at NP. Reload, nothing there, I think. Great. Okay. So what I'd like to do today then is go through the different sections of the book and tell you all what I find to be most compelling in each of those sections. The things I think that if you understand them well, then you really understand the material in the course. And that can help you figure out what to pay attention to as you get ready for the final exam period, which is going to be next week. Actually, I think we're actually going to be able to get out tomorrow, which would be wonderful. Give you guys extra time to work on it. I'm hoping we can give you a few extra days more than normal. I know there are 10 questions on the exam. Not that that really matters. There's lots of subparts. And I'm quite pleased with the exam because it teaches you some new things along the way. I hope that you find it informative and interesting. I certainly had some fun with the TAs, reading through them and putting them together. Okay, so we have a question here. Should we expect one problem per module, 10 modules in the finals? Last year's finals seems like an even distribution among all the modules. It depends on, we do have 10 questions. Yes, they are, yes, we try to hit all the modules. The thing is, we try to emphasize the stuff that you did not do assignments on. So, things like constraint satisfaction problems or Markov decision processes. Basically, the stuff that you did as assignments, we try to de-emphasize because you guys have already coded a lot of it. And I think that really gives you a good feeling of what's going on. But the stuff that's just in the book that we just had you read and look at the lessons, a lot of times when you read through the material, watch the videos, go, yeah, I get it. But until you actually do something with it, so you actually have to work a problem with it, you don't really realize you didn't understand what you were reading. At least that's what happens with me. And so we're trying to use this final exam period to As one final opportunity to provide some teaching by doing. And so you can expect more emphasis, even though there's 10 problems, there'll be more detail on the ones that you did not do assignments on. At least that's the goal. And let's see here. Yeah, so let's go through the modules. I actually have them here on my screen. This is kind of great, having done the online course, I am taking undergrads who want to work with me, and I say, if you really want to do stuff with silent speech recognition or sign language recognition or human activity recognition, just go see pattern recognition through time on my class, or start with machine learning or probability better and go on through pattern recognition through time. And it's really been a boon for my research in that I can get my students ramped up more quickly. But let me not get off subjects. Oh, the other thing, remind me, I wanted to describe to y'all how you can get involved in research after this class. So remind me if I don't say anything about it. All right, so first of all, game playing. So game playing is, again, one of my favorite things. We did an assignment on it. And as you know, that alpha beta is kind of, a really good thing to understand with node ordering, and how alpha beta pruning works, and how node ordering helps you reduce the number of nodes you have to look at. However, I think what really gets exciting there is Expectamax. We actually have probabilistic games, and that opens up a whole new set of games for you. Now, Expectamax is really interesting because you can only do shallow pruning, right? But knowing how to prove is a little bit sensitive, right? You have to think about it hard and do the math and make sure you're pruning properly. And remember that if you already have an 8 or something, and everything else is going to be less than or equal to 8, or depending on if you're doing min or max, you can ignore it, right? It's not just less than, or it's also equal to. So remember, you can prune when you're not going to improve your result. So game playing, alpha beta, Expectamax, pruning and Expectamax, that stuff is kind of exciting. 3-player games is fun, N-player games. Search, you guys got to do on a most intimate level. Of course, there, A star is what we really want you to know. That's often what people ask on in job interviews and that sort of thing. So I highly recommend understanding A star and admissibility and heuristics. That is powerful stuff. That'll come up again and again. Your tri-directional A star search. If you understand stopping conditions, well, if you just understand stopping conditions for bidirectional A star search, not even tri-directional A star search, you probably really have understood the material in that section. And remember, most surprising number of things in AI, not I'll say most, but a surprising number of things in AI can be thought of as just search in NP hard space. Okay, then we get into approximation algorithms and iterative improvement algorithms, and they include the lessons 3 and lesson 4. That's similarly annealing and constraint satisfaction. And there you have things like, backward checking, forward pruning, forward checking, backtracking, forward checking, most constrained variable, most, what's the value one? Most, not constrained, most constrained value, most constrained variable, and most, I've lost what it is now. I guess I could just look at the list of things here. Backtracking, forward checking, constraint propagation. There should be something arc. Whoop. Hey. Structure CSPs. We have arc checking too. Most constrained value. That's it. So those are good things to know. So how to handle structured CSPs, how to do those graphs, how to think about those things, how to do forward checking, constraint propagation, that sort of stuff is important there. Now with the things like constraints, one other thing we should talk about in there, I guess, is things like genetic algorithms, which is this evaluation of improvement, and also simulated annealing, right? So as I said in class, genetic algorithms are almost always the second best way to do everything, just because they take slower to converge. But they are extremely powerful in the sense that it's one of these things like neural nets. You can throw it at a problem, and most of the time you'll get a solution that's reasonable. And there's a lot of problems out there, practical problems in the world, where a genetic algorithm or a neural net will do it just fine. The question is, do you understand what the result gave you, right? And so the explainability is a little bit harder. Certainly with neural nets, it's harder. With genetic algorithms, it is also harder, but you can kind of see it converging a little bit more easier than neural nets. Simulated annealing, the idea of hill climbing, gradient descent, this idea of iterative improvement algorithms, the n queens problem, where you just try something and improve it. That is an important lesson there. And it's actually, I find it to be important in research too. Oftentimes when I have a new project and a new student, I'll just throw them at something, say, get something done, anything done. And we look to see what they've done. That helps define the problem. And then we iteratively improve it. So iterative improvement algorithms are not just for n queens. I find that thinking about research as iterative improvement algorithm is a useful thing too. Let's see here. Whoops, I didn't want to do that.
Speaking about saving
Go back. So anything else I want to say about simulated annealing section? Let's see here. Oh yeah, local beam search. Stochastic local beam search is really important because that's basically very similar to how we're going to do Viterbi in the future. And I guess that's something I should explain here. So you all have done in assignment 6, you look at Viterbi lattices and how to figure out which is the maximum path through that. If you use a forward background algorithm, you'll figure out the maximum probability through all paths to leading to a result. But in practice, you have a huge Viterbi lattice in any sort of real problem, whether it be speech recognition, handwriting recognition, anything like that. You got a huge lattice, and what you got to do is figure out which paths to take, and that's where local stochastic beam search helps. Basically, you're basically doing beam searching. You're throwing away things you don't think are going to work. Now, if you just keep the highest probability paths, you may not get the optimal answer because something may have really bad probability at the beginning and really good probability at the end. I'll give you an example. In sign language recognition, oftentimes when I'm dealing with kids doing sign language games, they might start out saying, they're supposed to say the green alligator under wall or something. And they'll go, green alligator under wall. And that false start, and the fact that they're starting to do blue and then they switch to green, or they say, no, then they'll switch to green. That really confuses the Viterbi lattice because the hand shapes are wrong. It doesn't know what it's doing. And so what we do, and so local stochastic beam search, what it'll do is it not only just takes the ones that are most highly probable, but it also kind of samples the rest of the space and keeps the samples with a certain probability of them being, the right path. And this way you can actually oftentimes get very good results in sign language recognition or speech recognition, where you're not doing the entire Viterbi lattice, you're just keeping the top end paths. If you try to get all the paths, you run out of memory on computer systems. And so local stochastic beam search, you start with your paths and a sample at either end, lower probability ones. And with a sign language recognition, that's really important because as that student is going, no green alligator under, right? All those paths are about equally probable. And you need to have at least some of the paths that are going to get you back into the green alligator under wall. Now, the magic trick that we figured out with this is instead of recognizing green alligator under wall, we actually recognize it in reverse, wall under alligator green. Because generally in sign language with these kids, generally by the time they get to the end of the phrase, they're no longer doing false starts or stammering. By the time they get to the end of the phrase, they're pretty clean. And so by starting at the end and recognizing backwards, we end up with much cleaner paths and much tighter, a much more constrained problem. In truth, though, most of the times we just solve the full Viterbi lattice because why not? Sometimes forward-backward helps too, but sorry, we're skipping ahead here. But local stochastic beam search is an important thing to recognize or to understand from section 3. We talked about genetic algorithms. Understanding the importance of crossover, understanding the importance of mutation in genetic algorithms is very good. Understanding how you can use simulated annealing to solve a local, to get you over a local minima or maxima, depending how you're doing things. If you're doing hill climbing, gradient descent, that's useful as well. And notice a lot of stuff you learned in section 3, things like gradient descent or the beam search, come back later on when we talk about neural nets or these HMMs. So this stuff actually nicely builds on each other. Okay, so yeah, there's something I wish I could do more assignments in that space, but there's only so much we can do. Probability, of course, is a basis for a lot of stuff. We'll give you a probability problem, and I'm very excited about the probability problem because I think it teaches some interesting stuff this time. So new AI coming in your probability problem. And basically what you really want to know here is things about, the notation, conditional independence, that sort of thing. Independence, what that means. So Bayes' rule, of course, is probably the most important thing to get out of probability. Going forward, what also is extremely useful is, of course, Bayes' nets. Bayes' nets was all the rage not that long ago, and it's a very useful technique, and it gets overlooked a lot by what's out there today. It is what's nice about Bayes' rule too is that you really can look at the nodes and look at causes and effects and see what gets activated, and it's explainable, right? It's a real probabilistic system that's extremely explainable, and it's if you can use one, I highly recommend it. Machine learning. Oh man, there's so much cool stuff in machine learning these days. And the big point here with machine learning is just having a selection of techniques under your belt so that you can apply them in real life. A lot of times, things like K nearest neighbors is just going to be good enough for you. It's a really simple method, and there's a lot of variants of K nearest neighbors, but it is surprisingly powerful when you have enough data for training. Of course, knowing about Gaussian distributions is useful. Central limit theorem, why we use Gaussians. Knowing about cross-validation, how to train and test a system. You have, suppose I have 100 examples of something. I take 10% out randomly, leave them aside. The question is why randomly, right? We don't want to take the first 10 or the last 10 or the middle 10 because they may not represent the entire data set. Maybe the person who's giving you the data is getting tired. Maybe you have multiple subjects and you don't want them all from the same subject, that sort of thing. So generally, almost all the time, you want to do random selection. So 100 samples, I take 10 out, pull them aside, don't look at them again until I'm done. And the rest of those 90, I might leave 10% out randomly. So say 9 of the 90 and train the other 81. And I tune my parameters, doing testing and training, doing n-fold cross-validation, where I have I do it, say 1,000 times, leaving 10% out, right? Because I have 9. 9, you choose 9, which is a huge number of combinations I can do. So I might take 1,000-fold cross-validation, training on 81, testing on 9, and getting my average result. And then when I have everything tuned and I think everything is best I can do it, then I take my holdout set and I test on that and I see what the results are. I'll give you an example on that. Currently in my research, we are trying to make a system. Actually, it's right here. I can show you research as it happens. I have a student with me, and this is an electrode array that you can put in your mouth. It has like something like 124 electrodes, if I remember right, 102, something like that. And it senses where the tongue is on the roof of the mouth. And so what we're trying to do is have people be able to spell silently. Now, why does that matter? Why would anybody want to speak silently to their computer? Well, for some people, like the physicist who had ALS, he had tracheostomy early on, and so he lost his ability to voice, but his mouth articulation was fine. And if he had a system like this, he could actually be able to communicate. Now, the thing is that Stephen Hawking had progression, but for where he finally didn't have good mouth articulation, but for many years he could have. So what Stephen Hawking could have done is put in this electrode array, and then if he wanted to type his book, he could simply just say, THE space BEGINNING space, that sort of thing. And it turns out you can do that quite quickly. The question is this electrode array good enough to do it silently where you don't have that voice, right? It'd be just like, etc. So what we're doing is we're collecting 1,000 phrases from a standard corpus, and then taking, and also unfortunately, doing these phrases is kind of hard. We make mistakes all the time. So we're keeping all the ones where we make mistakes on them and keeping them out as our reserve test set, right? And then we're training on those 1,000 phrases using n-fold cross-validation. Now let's train everything, and then we'll go back to the ones we messed up, chop them up so we just have the good parts, and testing on that as our holdout set. And that, given the results on that, that'll be a whole lot better than just trying to just do cross-validation itself without a holdout set. So I'm crossing my fingers. We have a deadline next week on this. We will see if we can actually do the silent spelling system for communication. If you're all interested in this, there was a previous system on this called Tongueboard that my student Richard Lee did. You can find video of me speaking silently at a conference, giving a lecture silently, at least the beginning of it silently, using this funky mouth array thing, electrode array. So yes, cross-validation is extremely important to know how to do things. Now, going back to machine learning, decision trees are extremely important. They're understandable. They're often one of the easiest things to do. Random forest, same way, which is just an extension of decision trees. Knowing naive Bayes and Bayes classifier, again, relatively simple stuff there. But each of these things have different pluses and minuses. For example, maximum likelihood is very good for any data that has sort of a convex hull around it, and the data is separable. K-nearest neighbors can work better when things are intertwined more. And of course, there's no free lunch. No one method is going to be the best, or I should say, no free lunch specifically says for every method out there, there is a problem for which it's optimal. Some methods work on more problems than others. And that's what we're trying to do here is give you an overview of the methods that we find to be the most useful. So we talk about decision trees, information gain, random forest. We talk about boosting. Boosting is extremely useful for feature selection. So is information gain, trying to figure out what features matter. So that's important. Neural nets, we go through backpropagation. Backpropagation is the underlying basis of a lot of neural net technology for the training. So knowing what you can do with backpropagation, especially with a perceptron versus a multi-layer net, that's a useful thing to know. And that's also, the difference between a perceptron and having hidden layers is a very good thing to know for things like interviews in industry. Talk a little bit about unsupervised learning, and you did a little bit on that in k-means and expectation maximization. Knowing the difference between unsupervised and supervised learning, knowing what they're good for, and knowing that unsupervised learning is much harder than supervised learning, is some of the highlights there. Going forward, so you guys all know that I love hidden Markov models. It's a technique I've used again and again. It often works much better than neural nets with less data, and often it helps with neural nets smoothing the data through time, because the neural net research has not really represented time as well yet as it could. So using a combination of HMMs and neural nets, which are both graphical models, seems to be the win currently. But I talk about Baum-Welch re-estimation. I talk about Viterbi recognition, and that's what you're looking at in assignment 6. But do not forget dynamic time warp. Dynamic time warp was out there for years and years and years before hidden Markov models took off, and they're still kind of the default thing to use if you have a simple problem. So dynamic time warp and HMMs is what we're trying to get out there. Logic and planning. So kind of like the highlight of logic and planning, well, highlight of logic to me is resolution on first order logic, right? Propositional logic resolution is really easy. Frankly, first order logic resolution is pretty easy too, but you have to know about how to get stuff in CNF notation, so you can actually do the unification that you need for resolution. So if you really understand resolution in first order logic, you know a lot of what's going on. And also you kind of get an intuition for the forward and backward chaining algorithms in logic. Planning is you have strips, you know how to do that formulation. A graph plan is kind of as far as we get in the book. Planning was so hard for so long that AI PhD students just hit the wall so many years on that, until our machines got fast enough and graph plan came along, we finally started getting somewhere on planning. So really what you need to know is the partially ordered plans, clobbering, the Sussman anomaly. If you understand that sort of thing and how to go from a partially ordered plan to a total order plan, how graph plan works, how planning works in general, that's great. And again, resolution for logic. Lesson 10, I wish we had more time on. Markov decision processes are extremely useful. Certainly partially observable Markov decision processes are extremely useful. When I first got to Georgia Tech, Sven Koenig, one of my fellow professors, was big on POM-DPs, partially observable Markov decision processes. And I wish I had learned more from him at that time. It was only really through teaching this course that I really started getting an intuition for it. But what you really want to know there is some idea about Markov decision processes, how they're trained, policies, learning algorithms, Q-learning, all that sort of stuff. Knowing what they're good for, knowing what the tricks are, knowing things about the rewards and the discounts, knowing how those algorithms work is extremely useful, just to keep in the back of your head in case you ever need it in real life, because they're very powerful algorithms. Okay, so that was me ranting about the 10 different modules and what I thought was important. Let's talk a little bit about where we about research. So research for OMS students is still a relatively new thing. We're still figuring out how to do it. For a while, I think my students counted for half of the OMS researchers out there, believe it or not, these people who are getting credit for it. And as a master's student, you can get 3 credits of unrestricted elective can go to your degree by doing research with a professor. However, just doing 1 semester worth of research is often doesn't give you the full experience. So even though it doesn't count to your degree per se, it still counts to your GPA. It still counts. Still counts as credits. So I highly recommend if you end up doing research with a professor over OMS to do it for more than 1 semester, because it can be a very rewarding experience. You can get to see whether or not you might want to get into this stuff as a PhD student or go into research more seriously. My students work on, as you know, Jack Watson, which is the anti-plagiarism stuff. We have work in matching up exams together, looking for plagiarism that way, which is a surprisingly interesting AI problem. Like most things, a little bit of effort got us 80% of the way there, but completely solving the problem is going to be forever. So it's very interesting research. We also have, of course, the stuff where we're looking at the homework for hire, installing our agents on all the different freelancer sites out there, and or the course help sites to make sure that people aren't hiring tutors for doing their assignments or midterms or finals. And then also we finally have something where we're trying to do a Blue Jeans channel that's permanently on, at least that's the hope. So y'all can actually interact with each other at any time over a conference call, get more of the peer learning done. And what we want to do there is have something that sits there in the background and looks to see when students pull up code, and then provide a warning for that. What we see in the literature for online learning is that having the honor code is fine, but what's more effective is actually having warnings when you actually see some behavior that is questionable, and that really helps keep the plagiarism and the cheating down. So that's Jack Watson. You guys know about Parker. That is one of our big efforts right now. Parker is hugely successful in the sense that Piazza now has their own version of Parker that they are running. So in other courses, you will actually see something like Parker. Unfortunately, it's not as good with HCI. They put it in the wrong place. They're not quite doing the right things. So we're talking with Piazza about improving it. But it's great that Piazza has adopted Parker or something like Parker in their own product. Now we're actually trying to improve upon it by helping the TAs and instructors give better responses, more quick responses, and try to figure out which posts are the most important. So that's what's going on in my research. And you'll see a call from us at some point, hopefully before the end of the semester officially, for who wants to join us working on the Jack Watson and Parker research. Okay, so now I have a question. Planning under certainty, the value iteration. Oh, I should finish up the research stuff. In general, if you want to work in research with a professor, go to their Google Scholar page, which is scholar.google.com. Type in the professor's name, order it by date, and see what they're working on right now and who they're doing it with. That's the best way to see if that professor is doing stuff in the domain you care about. And then start talking with their grad students or with that professor, see if they have any research available for you that you can do as an OMS student. Of course, the on-campus students have a great advantage because they can just ambush us after class and say, hey, I'm interested in this stuff. Here's our resume. But if you go approach a student over OMS right now, It's easier because most professors are having their office hours over blue jeans. Just say hi to them, and um, be sure to have your resume ready. You might be able to find some professors now that are more open to doing research in OMS. And my team is trying to put together sort of best principles for doing research with OMS students. We'll see how that goes. Again, Google Scholar is your friend on this. Try to figure out the professors who are doing the coolest work that really speaks to you. And again, don't look at it just as a semester thing and just do it for the credit. Look at it as something that's really going to help your career, help create a portfolio of interesting work, and expand your knowledge and your skill set, because nothing beats one-on-one mentorship with people who've been doing this stuff for most of their lives. Okay, get back to the questions here on live chat. MDP, in value evaluation, can the utility of a non-goal state become equal to or greater than the utility of a goal state? Depends if you have multiple goals. If you have multiple goals where one goal is like, say, 1,000, another goal is 100, certainly the value of the goal next to that 1,000 could be greater than that 100. But in general, if you only have one goal and it's 100, I do not. Well, I guess you could also have the negative goals, right? So if you're trying to avoid a certain end game, like falling down the pit in Wampus World, let's see here, the value of that. No, because the way the utility propagation works, you have a high negative. You still have the positive being propagated. So I'd say that in the case we have multiple goals of different values, yes, it's possible. In the case you have one goal of, and that's the highest value on the board, you shouldn't be able to get higher than that because you can't propagate a higher level out. Okay, I assume the utility of goal state is equal to the reward associated. The utility of a goal state is equal to the reward. The utility with that goal state is equal to. Okay, I think I've answered your question there. Hopefully, and I'm just doing this off the top of my head, hopefully that makes sense when you start doing policy iteration and utility propagation when you look at a map with that. So an easy thing to do is take the standard thing they have in the book, but make two goals. One's 1,000, one's 100, with a space in between them. Probably the space in between the goals is going to get somewhere between 1,000 and 100, which is bigger than 100 goal state. But then when you take that 100 away, it's clear you're not getting anything more than 1,000 on the board. All right, that's my intuition. So what is the typical time commitment for research? Generally, it is done in units. So a 3-credit course, which I think is what we are here, you multiply that by 3, and or we have 4 credit. Anyway, so if you do 3 credits of research, you're expected to do 9 hours of work a week on that research. If it's 4 hours of research, 12 hours, right? I have some students, what I encourage my students who are master students with me, I often encourage them to only take 2 real classes, like, 2 3-unit classes. That's 6 units. In order to maintain their full-time student, I have them take 6 hours worth of research with me. And so that involves, 18 hours of work a week in theory. In practice, the amount of work you do a week varies greatly. It depends if we have a deadline coming up, if you get really excited about something, there is some dependency coming up where somebody else is waiting on your work. So, I've personally done 80 hours of work on a project one week and none the next. But what you should do, what should average out to in theory, is 9 hours worth of work a week over those 16 weeks. So that's like 144 hours worth of work or something like that. In practice, though, you want the research to be something that you love so much, you end up spending more time than that on it, just because it's cool. Okay. So let me go back, make sure there's nothing else on Piazza. Nothing there. Look at the other piazza. Oh, we have another question. So, extra time on the final, given the delay in getting the A6 bonus published, can we get time after the final complete the bonus? It seems like there is less grading and disputes of the bonus the TAs will need to settle. Unfortunately, we can't do that. We are, by extending the date of the final as far as we did, we are going to be really hard pressed to get all the grades in on time, especially with any grade changes, that sort of stuff. The TAs and I are just going to be swamped. Unfortunately, given our systems, I still have to manually copy over grades from Canvas to Banner for our stuff. So unfortunately, it is we can't extend the bonus anytime on the assignment 6 or its bonus. All right. Is it possible to assist with research after graduating from OMSCS? Yes. Rocco, well, the official answer is no. But that's mostly because people are talking about doing research on campus, and they always are paranoid about somebody slipping and falling in the buildings. And so for insurance reasons, the official answer is no. For OMS, though, and practically speaking, yeah, I have students who continue doing research with me over Hangouts or over teleconference for years after graduation. One of my PhD students, in fact, right now, has gotten a grant with the Wild Dolphin Project, a Templeton grant, to continue our work on trying to find the femoral units of dolphin language in quotes, dolphin vocalization is what I should say. So yes, it's often possible to continue doing the research post-graduation. And in fact, what I find often in Silicon Valley is there's a lot of research scientists who work with at these companies, and they do their 9 to 5 job. They do their normal hours for the company, but where they become happy is actually doing research side projects, and that could be of all variety. But if you're going to do research side projects, you might as well do it on something real, something that makes a difference in the world. One way to do that is to align yourself with the universities. Sometimes you can just get a group of people together and go tackle a problem. But one of the biggest problems in research is knowing what is a useful problem, what is a good problem to solve. There's so much stuff in the world to do. What gives you the maximum impact? And that's part of one of the reasons why, grant funding and, National Science Foundation, all this process we go to where we ask for money from the government or from these companies or from these foundations for supporting our research. It's not just the money we're looking at there. It's also the peer review. Sometimes the best ideas actually come from your reviewers, and some of the best criticism comes from them too, where you realize, oh no, I shouldn't be looking at it this way, or actually, yeah, you're right, that is a dumb idea, or here's a better way to do it. So continuing, if you do research, I highly recommend aligning with somebody who's done it before, knows how to evaluate a problem. And I got some really good advice at Google, actually, from the head of research at Google, who said, whenever I have a new project that I think is really cool, I find these 6 people most likely to object to it. And I work with them until they believe it too. And once that happens, then I actually propose the project. And that's a pretty good model, right? Finding a good critic is extremely valuable. So if you're going to do research, find somebody who knows how to do it. Find somebody who knows how to determine which problems are most useful. And also, some of you guys are interested in entrepreneurship. What National Science Foundation has something called I-Core right now. NSF I-Core is basically, they're trying to do a scientific way to doing startups. And a lot of the methods we use in human-computer interaction in HCI, an HCI class, in fact, is what NSF is doing, is teaching to help entrepreneurship. And so what they're trying to show is you can have a great idea of something to do, but it may not be what people need. And they're trying to show how to direct research into things that will be most, well, in that case, most profitable, right? But you also do it for most social media. There's a lot of stuff I do in academia, like the sign language recognition research, like the brain braille stuff where we're trying to help people with ALS communicate after they get locked in. That has a lot of social meaning, but it's not going to make much money. Okay, so I've kind of got off track here. Are you open for our OMS students doing research with you? Yes. Matter of fact, you'll see an email coming out or a Piazza post, rather, probably after the final, asking for people to send their resumes for the work that we're doing. We'll generally post the jobs we have, generally posted by the PhD student who's running them or the master student who's running those projects, and you just respond to that with your resume and some background. Okay, so I see no more questions. I'm going to go grab some lunch before I have to go teach my hardware course. Yes, I'm actually doing a hands-on hardware course during quarantine. This is fun. But I have all my students with their toolkits and their hardware, and they're trying to finish up their skill demos before the end of the semester. And so I'm getting to do remote hardware diagnostics, which is fun. All right. Good luck on the final. Hopefully you're having fun with assignment 6. And if you're interested in research, look out for those messages that we hopefully will be sending out sometime in the next couple weeks. Thanks much, folks.